Hey everyone, in today's video we're going to be talking about stoichiometry and we're going to do gram to gram conversions. We're going to talk about the limiting reactant, the excess reactant, the theoretical yield, the actual yield, and the percent yield. So first we have a chemical reaction where ammonia reacts with oxygen gas to form nitrogen monoxide and water. And this chemical equation is balanced. So that means that we don't have to balance it. If it wasn't balanced, then we would have to balance it for stoichiometry. So we have 34 grams of NH3 and 80 grams of O2 reacting together. So we want to find which one of the reactants is the limiting reactant. The limiting reactant is whichever reactant runs out first. And once the limiting reactant runs out, then the reaction stops. So the limiting reactant determines the maximum amount of product that can be made. So we're going to convert each of these into grams of NO. So let's do 34.0 grams of NH3. First, we want to convert this into moles, so we would have moles on the top and grams on the bottom. So we have grams on the top, that means that we want grams on the bottom so that they can cancel. So we would do 1 mole of NH3 would be equal to the molar mass of NH3, which we can find on the periodic table. So it would be N, which is 14.00674 plus 3 times 1.00794. And we get 17.0306 grams of NH3. So we have grams on the top of NH3 and grams of NH3 on the bottom, so that means that they can cancel. Now, once we have moles of NH3, we want to convert moles of NH3 into moles of NO, which is what we want. So we would multiply this by the mole ratio, which can be found by looking at this balance equation. So we have 4 moles of NO, since there is this 4 here. So it'd be 4 moles of NO, which is just a coefficient that's before NO, over, we want the moles of NH3 on the bottom since the moles of NH3 are already on the top. So we would have also 4 moles of NH3. So that means that the moles of NH3 can cancel. And then we now want the molar mass of NO so that we can convert this to grams of NO. So the molar mass would be N, which is 14.00674 plus oxygen, which is 15.9994. And so we get 30.0061 grams of NO is 1 mole of NO. And so when we multiply the entire thing, we would get 59.9 grams of NO. So now we found this. Now we want to find the grams of NO made from the 80 grams of O2. So we'll do 80.0 grams of O2 over 1. We want moles on the top, so 1 mole of O2. And we want grams on the bottom so that the grams can cancel. So it'll be 2 times 15.9994, which is 31.998 grams of O2. And then we can multiply by the mole ratio to convert from moles of O2 to moles of NO. So we want moles of NO on the top. We have 4 moles of NO. And we have 5 moles of O2, since there's a 5 here. The moles of O2 would cancel, and then we would want the molar mass of NO, which we already calculated to be 30.0061. And that would be equal to 1 mole of NO. So now that moles can cancel, and that would give us the grams of NO. And so we can just type all of this into our calculator. And when we do, we would get 60.0 grams of NO. So the limiting reactant is going to be the one that has the lesser amount, which is going to be this one. And so this would be our answer of how many grams of NO are formed, because we want to find the one that the limiting reactant determines, which is NH3. So the limiting reactant would be NH3, and the excess reactant would be O2. So next we want to find how many grams of H2O are produced. So we would first start with the amount of the limiting reactant, which is NH3. So we have 34.0 grams of NH3. And then we would convert this to moles of NH3. And we already calculated its molar mass, which is 17.0306 grams of NH3. On the top, we would have how many moles of H2O, which is 6. So we have 6 moles of H2O over the amount of moles of NH3, which is 4. The moles of NH3 would cancel, and then we would do the molar mass of H2O on the top, which is 2 times 1.00794 plus oxygen, which is 15.9994, which would equal 18.0153 grams of H2O. And then we would have moles of H2O on the bottom so that they can cancel, and we get, when we type all of this into our calculator, we get 53.9 grams of H2O. So to find how much of the excess reactant is left over after the reaction is complete, we would first start with the limiting reactant, which is NH3, and we have 34 grams of that. We want to convert it into moles of NH3. So we would have, on the bottom, we would have 17.0306, which we calculated here. So the grams of NH3 can cancel. And then we would multiply this by the mole ratio. So we want to get this into the grams of the excess reactant, which is O2. So we want to convert grams of NH3 to grams of O2 because O2 is the excess reactant. So we would do moles of O2 on the top, and we have 5 moles of O2. And we want moles of NH3 on the bottom so that they can cancel. And we have 4 moles of NH3. And then we multiply by the molar mass. So we have 31.9988 grams of O2. Oops. Which is 1 mole of O2. And the moles of O2 would cancel, and that would give us the grams of O2 that was used in the reaction. So when we type all of it into our calculator, we would get 79.9 79.9 grams of O2. So this is how much grams of O2 that we actually used in the reaction, but we want to find how much is left over. So we would do the amount that was the total amount of O2, which is 80.0 grams, minus the amount that was used, which is 79.9 grams. And when we type that into our calculator, we get 0.1 grams of O2 left over after the reaction was complete. So next we want to find the actual yield of NO. We want to find the percent yield of NO. So the percent yield oh my god. Okay. The percent yield is equal to the actual yield over the theoretical yield times 100. So the actual yield is the amount of product that you actually get when you do an experiment in the lab. So it's going to be less than the theoretical yield because you're going to lose some of it in an actual experiment. But the theoretical yield is the amount that you would get if you did an experiment with everything going perfectly, which is not going to happen. So that's why the actual yield is always going to be less than the theoretical yield. So the percent yield, the percent yield will equal the actual yield, which is given 40.0, and this will always be given over the theoretical yield of NO, which we already found was 59.9 grams, times 100. So when we type that into our calculator, we would get 66.8%. And the percent yield tells you how much of the theoretical yield you actually made in the experiment. So for our second example, we have solid aluminum reacting with iron 3 oxide to produce iron and aluminum oxide. So this is a balanced equation. And if it wasn't balanced, then we would need to balance it, but it is balanced, so we can move on to the next step. So we have 50.0 grams of Al and 80.0 grams of Fe2O3. So we want to find the limiting reactant, uh, which is going to be either Al or Fe2O3. So we have to convert both of these to grams of Fe to find which one gives the lesser amount. So we have 50.0 grams 50.0 grams of Al over 1. And then we want moles on the top and then grams on the bottom so that they can cancel out. So like we want grams on the top and then grams on the bottom of aluminum. So 1 mole of Al is going to be on our periodic table, we would see that it would be 26.981,538 grams of aluminum so that they can cancel out. And then we would multiply by the mole ratio. So we were wanting to find grams of Fe, so we would have moles of Fe on the top. We have 2 moles of Fe, so it would be 2 moles Fe over the moles of aluminum, which is also 2. So we have 2 moles of aluminum on the bottom so that they can cancel out, one on the top and the other on the bottom. And then we want to find the molar mass of Fe on the periodic table, which is 55.845 grams of Fe. We want moles on the bottom so that they can cancel out, and that would give us the grams of Fe, which is what we want. And then we would just type all of this into our calculator to find grams of Fe, which gives us 103 grams of Fe. Next, we want to convert 80.0 grams of Fe2O3 to grams of Fe. So we have moles of Fe2O3 on the top, which is equal to the molar mass, which is 2 times Fe, which is 55.845 plus 3 times 15.9994. And that gives us 159.688 grams of Fe2O3. So that grams of Fe2O3 can cancel. We want grams of Fe, so we would have moles of Fe on the top. So we have 2 moles of Fe, and we want moles of Fe2O3 on the bottom, and we have 1 mole of Fe2O3 since there isn't any coefficient out here. That's just a 1. So it would be 1 mole of Fe2O3. And then we want the molar mass, so on the top, which is 55.845 grams of Fe on the top, and 1 mole Fe on the bottom so that they can cancel out. This is always going to be 1 if it's with grams on the top or bottom. So 80 times 1 over 159.688 times 2 times 55.845 gives us 55.95, which is just 56.0 grams of Fe. And so since this is the lesser amount, this would be the grams of Fe that are formed, because the limiting reactant is Fe2O3, and once that Fe2O3 runs out, then the reaction stops. The excess reactant is aluminum. Next, we want to find the grams of Al2O3 produced. So we would look at the limiting reactant, which is Fe2O3, and we had 80 grams of that. We want moles of Fe2O3 on the top. It's always going to be 1 when we have grams. So it would be 2 times, oh wait, we already have this. Yeah, we have this, it's right here, so it's 159.688 grams of Fe2O3. The grams can cancel. And then we want Al2O3, and we can see that there is no coefficient, so it's just 1 mole of Al2O3 on the top. Oh, wait. And then we want to find the moles of Fe2O3, which is also just 1. We want moles of Fe2O3 on the bottom so that they can cancel out. So since these are the same on the top and bottom, they can cancel. And then we want the molar mass. And we want grams on top and moles on bottom so that moles can cancel. So it'd be 2 times Al, which is 26.981538, plus 3 times 15.9994, which is 101.9613 grams of Al2O3. over 1 mole of Al2O3 so that the moles can cancel. And that would equal the grams of Al2O3, which is what we want. So we can type all this into our calculator. And we would get 51.1 grams of Fe2O3. So now we want to find the amount of excess reactant left over after the reaction is complete. So to do this, we would start with the limiting reactant, which is Fe2O3, and we had 80 grams of that. So we want moles of Fe2O3 on the top, so that we have grams on the bottom so that they can cancel out, and we just found this here. So now the grams of Fe2O3 can cancel out, and then we would convert. So we want grams of aluminum, which is our excess reactant, and we have 2 moles of aluminum, which can be on the top, because we want moles of Fe2O3 on the bottom, and we just have 1 mole of that so that they can cancel out. And then we find the mass, and we want grams on top, so we would look at aluminum on the periodic table, and we have 26.981538 grams of aluminum on top and 1 mole of aluminum on bottom. The moles of aluminum cancel, and we get, when we put all this into our calculator, we would get 27.0 grams of aluminum. So this is the grams of aluminum that was used in the reaction, but we want the amount that was left over after reaction was complete. So we would look at the original amount, which was 50.0 grams. Minus the grams that was used, which is 27. And that would give us the amount that was left over, which is 23.0 grams of aluminum. So finally, we want to calculate the percent yield. So remember, percent yield is equal to the actual yield over the theoretical yield times 100. So we would have the actual, which is given to us, which is 45.0 grams of Fe, over the theoretical yield of Fe, which we found here was 56.0, times 100, which would give us our percent yield, which is 80.4. Okay, 80.4%.